Let's continue to talk about how to write and find the two's complement for the binary number. Like in the previous video we talked about, we need to understand, usually we only have positive number, or we talk about unsigned number. Negative number actually came from we short about the same value of the positive number. A positive number and a negative number with the same absolute value, when they add together, will be equal to 0. That's an important concept about the negative number in math. Earlier, we learned about how to convert binary number between decimal number. That's only happen with the unsigned number. So that's why you can see if the decimal number equal to 1, we will represent binary number in a byte with 8 bits. So that's the 1 represent in the binary number. Now you will ask, how should I represent and find the binary number for -1? Honestly, we have no clue to represent binary number for the negative number, because how we display the negative number. And also the most important thing for the negative number, we need to make sure with the same absolute value, a positive number and negative number, they will add equal to 0. That came from the two's complement. So that's why here, let me show you. The -1 in decimal representing binary actually is 01 in the 8 bits. I will show you later how to find this one. But the first thing, let me prove to you that's correct. So then you can see here, if I try to add 0001, add with all the 80, you see, because you carry over 11111, right? So then the 8 bits, they will become 0. So that's why we see here, right? 1 plus -1 equal to 0, right? So that's why here the binary number 1 plus the binary number -1 equal to 0. So that's what we call the two's complement, because they need to meet the requirement for the math. Then we design the negative number to represent in the binary number. So this one we call the two's complement, because they need to add equal to 0. So here that show you how we will find the two's complement for the specific number. So start with the 1. If you have the positive number 1, you want to find the -1 in the binary system. The first thing, you need to revert all the bits. So that's why you can see here we have 70 and 1. We just revert this 70, all become 1. 1 becomes 0. So when we say reverse, that means if you are 0, I reverse become 1. If you are 1, reverse becomes 0. After you are done, plus 1 from the step 1. So then you can see here we add equal to 1. Then we got our two's complement number. So that's how to find the two's complement. And the two's complement actually is you finding from your original positive number how to find the equivalent negative value. So here you have 2 steps to do that. So of course at the end we prove to you, yeah, that math is correct. Why we need to have two's complement? The first thing, we want to find the binary number to represent the negative number. The second thing is earlier I talked about. That's because for the sign binary subtraction, sometimes you have a number 12 minus 3. Because using the bigger number minus smaller number, then right, our subtraction just need to borrow, then we are good. But sometimes if you have a number, for example, 5 minus 9. 5 is smaller than 9, right? How can you do the 5 minus 9 using the subtraction? Right, so on the other hand, we not really can do 5 minus 9. Instead, we do 5 plus -9. So that's why you can see here, you have 5, right? That's 101. 9 is 1001. When you try to minus, you didn't know how to borrow. 1 minus 1, 0. 0 minus 0, 0. 1 minus 0, 1. But when you have 0 minus 1, how to do that? Where did you borrow? You see, you have no way to borrow, so that's why you don't know how to do 5 minus 9. So that's why when you have a smaller number minus a bigger number, direct do the subtraction, it doesn't work. So that's why instead of we do the 5 minus 9, actually equal to 5 plus negative 9. Right. So you cannot do this way. This way actually is no way to do. Yeah, we don't know how to do the subtraction. But right, the one thing is you need to do 5. So here instead minus, you do the plus. Okay. So you do the plus sign, but one thing is you need to use the 5 plus negative 9. So the first thing you need to find how to find the negative 9. So we need to know negative 9, how to represent that. So we know 9 is 101. So remember earlier we told you 2's complement, how you will do that. So the first thing you need to know 9. So 9 is 00001001. So the first step for the 2's complement, remember here we show you 2's complement, this first step, reverse all the bits. Then we add 1 to the end. So that's why here negative 9, since we know 9 equal to this. So the first thing we reverse all the bits. So the first 4 is 1. Then here 1001 become 011. So 1001 become 0110. So that's the step 1, right? So don't forget, then at the end you need to do the plus 1. So that's why plus 1. So then you got the still 111141. Then you have 0111. Then you have the step 2. Then this one is your negative 9 in the 2's complement. So after we got the negative 9, so that's why here we do the plus. So then you can see here your 5 is 101. We plus negative 9. So then we use the digits to add 1 by 1. 1 plus 1, 0. Carry over 1. 1, 1, 0. Carry over 1. So 1, 1, 1. So we carry over 1. Then we need to still have 1 here. You carry over 1. So then you have the rest of that is 4, 1 here. But this one you may not see what's that value. But we know 5 plus negative 9 equal to negative 4. So later you will find out actually this value is negative 4. How to know this one is negative 4? Of course, this one is the 2's complement, right? So this number is negative 4. In order to make sure this number is negative 4, on the other hand, you need to have this number to find the 2's complement to make sure this value is negative 4. So here that shows you how to find to prove this number actually is negative 4. So we have this number. To find the 2's complement, first step, you need to revert all the bits. So that's why we got 6, 0, and 1, 1. Then second step, we need to plus 1. So that's why after 1 plus 1, 0, carry over 1. 1 plus 1, carry over 1. So that's why the 2's complement for this 6, 1, and the 0 is equal to 1, 0, 0. So it's not this value equal to the positive 4. So that's why we know this number is negative 4. So that's review again. So I just want to let you know why we need to have the 2's complement. That's because we need to find a way to represent decimal negative number in the binary system. And in order to find the 2's complement, the mathematical rule, we need to make sure the negative number plus the corresponding positive number, they will add to 0. So to convert to the 2's complement, you have 2 steps. The first step, you convert the original bit, reverse each original bit. That's the first step. Then second step, you add 1 to the end. So then you find your 2's complement. So the 2's complement not always using for the subtraction. Because one thing is, for example, if you have a bigger positive number minus smaller positive number, yeah, we can just do the subtraction, right? You can just borrow and subtract. However, sometimes if you have a smaller positive number minus bigger positive number, honestly, you don't know how to do the subtraction. So that's why in the binary system, you need to convert. Instead, you do the subtraction, you do the addition. So you make the bigger number you want to subtract become you plus their 2's complement. So that's how you will do the subtraction for the number you want to minus is bigger. And you will make sure their math result won't be destroyed. So they always have the correct mathematical calculation. Because as a hardware calculation is very important, that's why we can make sure their result won't be wrong. Yeah, so that's the 2's complement for binary system. So 2's complement, actually, the definition just means we try to find the equivalent value but with different sign. So if you want hexadecimal, actually you do have the 2's complement as well. So the rule will be the same. You just make sure you revert all bits, then add 1. But earlier when we have binary system, because we only have 1 and 0, so you know you can reverse between each other. But in the hexadecimal, since we have 16 different values, so the reverse bit actually is look like this. You have number from 0, 1, 2, 7, but the reverse bit actually like this. So you can see each reverse pair, they add to 15. So that's why 0 reverse is F, 7 reverse is 8. But you can see no matter which one, if they are reverse bit, they add become 15. Yeah, you see 3 plus C is 12, so that's 15. So here you will see an example. If you have the hexadecimal is 6A3D, in order to find the 2's complement, the first thing we reverse. So you can see you can use this table. 6 reverse is 9. A reverse is 5. 3 reverse is C. D reverse is 2. So after you have all the reverse, don't forget you need to add 1. Then you will get the result. So that's the same thing for the 2's complement. You also have the reverse bit you can refer to. So the same thing, please pause the video to see can you find the reverse 2's complement for 95C3. Then you can check if your result is correct. So that's very interesting because sometimes if we only have 1 byte value, according to you define this 1 byte location, but you need to tell us that's unsigned or signed value. So that's why sometimes when you have the same bit, for same value for each bit, for signed and unsigned, they represent different value. So you can see here, 0, 0, 0, 0. When signed and unsigned, right, they both equal to 0. But you can see here, if we are if we are positive, then you can see they are all the same. Because you can see the signed bit all equal to 0. That means we know they are positive. So from 0 to 127, they are all okay. But one thing is, once you have your 1 become the signed bit, so then according to this one is 1, then 7, 0, right? If they are unsigned or signed, their value represent differently. If this one is the unsigned integer, they represent positive 128. But if this one is a negative, is a signed value, they are actually represent negative 128. So you can compare all the negative number. That means your signed bit is 1, they will represent differently in the unsigned integer and the signed integer.